All of you welcome in our sixth period of mathematics paper 2 Laplace transformation. In previous period we have seen the example using the theorem of Laplace transform. Using theorem of Laplace transform of derivative, find Laplace transform of cos t and Laplace transform of t sin t. We find the Laplace transform of cos t in previous period. Now find second example. We will try for second. Laplace transform of t sin t. Here we have take f of t equal to, let f of t equal to t sin t. Therefore we find the derivative f dash of t equal to, by product formula, first into derivative of second cos at into a plus second function sin at into derivative of cos 1. Again take the second derivative f double dash of t, first into derivative of second minus sin at into a, therefore a square plus cos at into a, therefore now we have the product formula here, first second function first into derivative of second plus second function cos at into a into derivative of first 1 plus derivative of sin at cos at into a. Now a cos at we have twice, therefore minus a square t sin at plus a cos at plus a cos at twice a cos at. They will find f of 0, put here t equal to 0, f of 0 we have 0 sin 0, 0 sin 0, therefore 0. Then f dash of 0, in the derivative f dash of t, put t equal to 0, here t cos 0, therefore in first term 0, second sin 0, 0, therefore this is 0. Then by using the formula Laplace transform of f dash of t, f double dash of t equal to s into Laplace of f of t minus s into f of 0 minus f dash of 0. Now we know that Laplace of f of t is f of s, therefore we make here Laplace of f of t equal to f of s. Therefore Laplace of f double dash of t, put the value of f double dash of t minus a square t sin at plus twice a cos at equal to s into Laplace of f of t, we put here f of s, s into f of s, f of 0 is 0, f dash of 0 is 0, minus s into 0 minus 0, since Laplace of f of t equal to f of s. Now this Laplace of f of t equal to f of s, you use this idea in the previous example, that is first example of this cos of at. In the previous example you put here Laplace of f of t equal to f of s instead of using the previous formula. Here we have to take f of s then solve. To try the previous example by taking this Laplace of f of t equal to f of s in the formula, then you solve the previous example. Now separate this minus a square Laplace of t sin at plus twice a Laplace of cos at equal to s into f of s. Now there is f double dash of t, there is s square, not s, s square, s and f dash. Therefore s square into f of s is 0. Then minus a square Laplace of t sin at, that is Laplace of f of t, we write it as f of s, plus twice a Laplace of cos at, you know the Laplace of cos at, s divided by s square plus a square equal to a square into f of s. Now we can take common f of s from the two terms. Therefore f of s common, we get minus a square minus s square. Now take this term on the right hand side, minus twice as divided by s square plus a square. Now we can take minus sign common here and cancel the minus sign from both sides. Therefore we have f of s into s square plus a square equal to twice as divided by s square plus a square. Then we have to find f of s, therefore divide s square plus a square on both sides. Therefore we have f of s equal to twice as divided by s square plus a square divided by s square plus a square. Therefore we have square of s square plus a square. Now f of s means we have Laplace of t sin at, Laplace of t sin at equal to twice as divided by s square plus a square, square of this. This is the required transform of t sin at by using the formula of Laplace transform of derivatives. Now in the previous example, you solve the previous example, and that is the f of this example by using this formula. Laplace of f double dash of t equal to a square into f of s minus s into f of 0 minus f dash of 0. Instead of taking here Laplace of f of t, you can take here f of s and try to solve by this procedure. Then we see the next article. Laplace transform of integrals. Next article we see Laplace transform of integrals. There is one important theorem. Read the statement of the theorem. Let Laplace of f of t equal to f of s if f of t is piecewise continuous piecewise continuous on every finite interval, on every finite interval in the range t is positive, t is greater than or equal to 0, and it is of exponential order. It is of exponential order, so that there is constants. So that there exists constants m alpha t such that mod of f of t is less than or equal to m into e to the power alpha t for s greater than alpha, and for all t positive, then the statement of the theorem, then Laplace of the integration from 0 to t f of u du equal to f of s divided by s. Here f of s means Laplace of f of t. Therefore, Laplace of the integral is given by this formula, f of s divided by s. Now, see the proof of the theorem. Now, what is given that f of t is piecewise continuous on every finite interval in the region. In the range t is greater than or equal to 0. Therefore, write this. Let f of t is piecewise continuous on every finite interval in the range t is greater than or equal to 0. This is given us in the theorem. Therefore, it is integrable. Therefore, f of t is integrable. Therefore, we consider g of t equal to integration of this f of u du. Since it is integrable, we write let g of t equal to integration 0 to t f of u du. Therefore, we find g dash of t, derivative of this g dash of t. Now, derivative of the integration, we get the original function, that is we have f of t, and g of 0 means for t equal to 0, 0 to 0, if the limit is 0 to 0, we get the value of the integration equal to 0, g of 0 equal to 0. Then we have g dash of t is piecewise continuous. Then g dash of t is piecewise continuous except for points at which f of t is discontinuous. F of t is discontinuous. Therefore, Laplace of g dash of t exists. Therefore, Laplace of g dash of t exists. I use the formula for Laplace transformation of derivative. We have therefore Laplace of g dash of t equal to s into Laplace of g of t minus g of 0 by using the Laplace transform of derivatives. Therefore, we have s into Laplace of g of t. G of 0 is 0 by this equation 0, since g of 0 equal to 0. Now I put here value of g of t. G of t is nothing but the integration 0 to t f of u du. We put this value from equation 1. Laplace of g of t, that is Laplace of integration 0 to t f of u du, and g dash of t equal to f of t. Therefore, in the left hand side we have Laplace of f of t equal to s into Laplace of value of g of t integration 0 to t f of u du, since by equation 1. Now we know that Laplace of f of t is denoted by f of s. Therefore, I write here f of s equal to Laplace of s into Laplace of integration 0 to t f of u du. Therefore, we find the value of this Laplace. Therefore, Laplace of integration 0 to t f of u du equal to f of s divided by s. We are dividing by s. Therefore, this is the required formula, required theorem. Laplace of the integral is given by f of s divided by s, where f of s is nothing but Laplace of f of t. Laplace of f of t equal to f of s. Now we take example. Find Laplace of integration 0 to t sin s 3t sin s 3t dt, and verify the result by evaluating the integral, and verify the result by evaluating the integral. I use this formula. Solution. In the book, this is short example, but there is mistake in the book. No, there is wrong formula for sin h 3t, Laplace of sin h 3t. So we have Laplace of sin h 3t. Here I take the function f of t equal to this, let f of t equal to sin h 3t. Therefore Laplace of f of t equal to Laplace of sin h 3t equal to Laplace of sin h 3t, which is the hyperbolic function. Therefore the formula is a divided by h square minus a square, this formula. Now here a equal to 3, therefore 3 divided by h square plus 3 square, that is 9. Now this is nothing but f of s. Now in the book there is mistake, there is written as the formula for hyperbolic is minus sign, there is minus sign. Now there is mistake in the book, they are written s square plus 9, but by the formula there is s square minus 9. By using the formula, Laplace transform of integration 0 to t f of u du equal to f of s divided by s. Therefore Laplace of integration 0 to t sin h 3t equal to f of s divided by s. F of s given by this 3 divided by h square minus 9 divided by s. Therefore we write here 3 divided by s into h square minus 9. I prove this result by using the integration we have integration 0 to t sin h 3t dt. Now integration of sin h 3t, we have cos h 3t divided by 3, limits from 0 to t. Here 1 by 3 is constant, upper limit t, lower limit 0, t equal to t, t equal to 0. Therefore cos h 3t upper limit minus lower limit cos h 0. Cos h 0 is 1. Therefore we have 1 by 3 into cos h 0 1, therefore cos h 3t minus 1. Then we take Laplace of this. Therefore Laplace of 1 by 3 cos h 3t minus 1 equal to 1 by 3 constant, cos h 3t, Laplace of cos h 3t, s divided by h square minus 9, Laplace of 1 by s, since Laplace of cos h dt, it is given by the formula s divided by h square minus a square, this formula. Now simplify this, 1 by 3, here take the LCM, s into h square minus 9. Now here plus h square minus h square plus 9, h square cancel, 3, 9 by 3 we have 3. Therefore 3 divided by s into h square minus 9, equation 2. Now you can observe that from equation 1 and 2 the right hand sides are equal. Therefore we verified the result by using the integrals, by evaluating the integrals. Therefore from equations 1 and 2 the result is verified.